I'm Anil Kumar. Welcome to my series on calculus. Here is a very important video in which we are going to discuss fundamental theorem of calculus. So as you know, fundamental theorem of calculus has two parts, part 1 and part 2. We'll have fairly good idea about these two parts in this particular video. My approach is going to be very simple and basic so that many students who are relatively new to the topic can understand, right? Especially those who are doing GCSE level A, they'll be able to understand and apply the concepts very well. So in this particular video, we'll discuss how the derivative of area and function are related. Area under the curve is basically integration. The fundamental theorem of calculus part 1 will find definite integral concept in this particular video. We'll also discuss the fundamental theorem of calculus part 2. Right? So part 2, and then we'll take up application question based on velocity. So let's begin with the concept of area. So we have taken a very simple example. We'll consider a straight line and find the area under the curve between 2 points. So example here is, find the area of the shaded region shown under the curve of f of x equals to 2x plus 1. Area is bounded by the vertical line x equals to 1 and the moving boundary x equals to x above the x-axis and below the line, right? So that is the concept. So what we have done here is we have taken a function which is a straight line 2x plus 1. Let's try to understand the boundary conditions. When we say x equals to 1, we're talking about one side of it. This is x equals to 1. We just fixed it. The other one is a moving boundary x equals to x. So we have taken a point P. Let me write it slightly bigger here. So we have taken a point P in this case whose coordinates are x and y, correct? So that's a general point. So point P is free to move. So at present we are showing it at this particular position. That is the position. Now as P moves, the area increases or decreases, right? So let us say that the area is A of this particular shaded region. So we know that A is proportional to the position of P, right? So A depends on the position of P. Is that okay? Further away, P is from this particular point, more the area, correct? So it really depends on the position of point P. Now, to find the area, what we can do is we can do a small construction here, or you can think about it like a trapezoid. So we have two parallel sides. These are the two parallel sides, correct? And that becomes the distance between these two parallel sides. So we can find the area function from here, correct? So we have this side which is at 1 and here this is x, correct? P is xy. So we have x equals to 1 and x equals to x, correct? Now what is the area of a trapezoid? Area of the trapezoid is half of sum of the parallel sides length. These are the two parallel sides. So we'll add them up, AC and PD, and multiply by the distance between them, which is CD. Now in this particular case, the area function A of x will be half of, now A to C is this parallel side, right? This parallel side is at 1, the value of the function, that is f of 1, correct? So we'll substitute 1 in the function, get f of 1. And at x, it is f of x. Perfect. And now the distance between these two is x minus 1. So that is how we get the area function for the trapezoid in this particular case. If I substitute 1 here, then f of 1 is 2 times 1 plus 1, which is 3. So f of 1 is 3. F of x, we wrote 2x plus 1 as such. multiplied by x minus 1. Simplify this particular expression, it becomes 4 plus 2x, 3 plus 1 is 4, right? And then we'll expand and simplify the expression 4 plus 2x times x minus 1. We get 4 times, we just do distributive property here, so 4x minus 4 and then 2x squared minus 2x. So that is these four terms, combine them together, and what we get is a quadratic function. Simplify by dividing by 2, so we get the area function, which is equal to x squared plus x minus 2. Correct? So we have our area function ax is x squared plus x minus 2. Now see, compare the derivative of this area. So if you find the derivative of this area, what do you get? Let's do the derivative. So dA dx will be d dx of the area function, which is x squared plus x minus 2. Now the derivative will be 2x plus 1, correct? Do you see what 2x plus 1 is? Well, 2x plus 1 is the function itself. So what we notice here is that the derivative of the function area is equal to the function itself. And now we have a differential equation here, right? We have a derivative function and we have the function on the other side. Now this differential equation can be solved by integration, antiderivatives, right? So we get the area function, which can now be written as equal to integral of f of x dx, correct? So we'll solve this differential equation by integrating, right? So when you integrate, then you get a of x is equal to the integral of f of x dx. So that is a huge relation between the derivative, do you see, and the integral, do you see? So two problems. When we talked about derivatives, we were saying what? Slopes, right? Gradients. So derivatives means gradients. And now we're talking about integrals, which represents area. So see how they are connected. So we have connected gradients with area with this particular equation, and that results into the concept of fundamental theorem of calculus, correct? So we'll explore this. We took a very simple example of a straight line, basically to understand the concept. Now let's take a general curve and see whether it really works or not, right? So in this particular case, I've just taken any function here. So f of x is my function. Now in example 2, find the area of the shaded region shown under the curve of y equals to f of x, any general function, where the point P and R are extremely close. So we have taken 2 points here, P and R. So P is right there and R. So these are the 2 points to be considered, right? So we have these 2 points P and R, which are very close. That means that the distance between them is delta x, correct? So that is what we're trying to say. Now, if they are very close, well, the y values will be let's say delta y difference, and this is x and y. So we're taking this point P as xy, right? So okay, we have written here. So let the coordinates of these points be, P coordinates is pxy, and the r coordinates be are x plus delta x. So that gives you a space between the 2 points. Horizontal is delta x, right? And y plus delta y. So delta y was this particular space here, right? Okay. So that becomes the difference. So this is y for us. Okay, that makes sense. Now, we need to find the area of the shaded region. How do we figure this out? So we'll do it by squeezing it into two rectangles. You can very clearly see here we have two rectangles. One, the smaller one, which is shown here, and the one which is a bigger one. Let me show it with a different color. So which could be this one. So our rectangle which is shaded is in between these two rectangles. Now let's find the area of the other two rectangles. We know the area of our, let it be delta A, right? So we'll say delta A is the area of the shaded region. So this is delta A for us. Is that clear to you? So delta A is between the smaller rectangle whose sides are y times delta x, right? So sides are y delta x. And on the other side, the big rectangle, which is y plus delta y times delta x. So the area of the shaded region is in between these two areas, correct? Now, let's divide by delta x. What do we get? We get y on one side and y plus delta y on the other side, delta a over delta x right in between. Now when delta x is very small, approaching 0, then delta a over delta x, where limit delta x approaches 0, it is dA dx. That's the definition of derivatives, correct? So as delta x is approaching 0, delta a over delta x is approaching dA over dx. So that's the derivative. And now see, when delta x very small, delta y is also going to be very small, right? So in this particular condition, as delta x approaches 0, delta y also approaches 0, right? So in that case, the right hand side approaches y. So we have dA dx is sandwiched between y on one side and something approaching y on the other side. So from both the sides, they are approaching y, and therefore the value dA dx will be equal to y. So here we have derived the rate of change of area is y itself. And what is y? Y is the function, right? So in this case, we know y is the function, right? Which is general function f of x. So in a way, we have related the rate of change of area with the function itself. You get the idea. So rate of change of area under the curve is equal to the length of the moving boundary. So y is the y value, correct? So it is the length of the moving boundary. So if this is the boundary which is moving, then rate of change of area is basically equal to the length of the moving boundary. So that is the conclusion at this particular stage. And this is referred to as the fundamental theorem of calculus part 1, right? So we'll actually give it a formal definition which is written here. So we write the fundamental theorem of calculus part 1 is that if f is a continuous function on a closed interval a to b, then the function capital F defined by capital F of x is the integral of f of t d of t, where x is between a and b, is continuous on a closed interval a and b and differentiable on open interval a and b, and f dash or f prime equals to f, that is their antiderivatives, correct? So that is what the fundamental theorem of calculus part 1 is. So it basically states that the antiderivative f of x is equal to the integral of f of t, correct? Now that is very important to notice here, is that the f of x, when we are saying, look here, we have a function f of x, correct? And then if you see the integral is from a to x, and the function inside is f of t dt, correct? So what do you notice here? You notice that the area function which we are talking about, this particular area function, is actually dependent on the boundary, moving boundary, a to x. You get the idea, right? So that is what is the relation. And this was observed by the teacher of Newton, who is Sir Isaac Barrow. So he actually noticed this connection between the derivatives and the area, and later it was exploited by Newton and Leibniz. So, who actually formally developed this part of calculus and these two fundamental theorem of calculus. So that's a huge importance, correct? Now let's move forward from here, take up some examples to solve area related questions, right? So now our example 3 is finding area under the curve. So example 3 is find the area of the shaded region shown under the curve y equals to 3x to the power of 5 plus 3 between x equals to minus 1 and x equals to 2. So that is our value of minus 1, and 2 is somewhere beyond, right? Let's say 2 is somewhere here, correct? Now, as we did the derivation, we'll take a point, general point P, somewhere in between A and B, right? So the idea is this is the A value, this is the other extreme B. So somewhere in between, we'll take a point P, right? And we'll find the area function within that interval. And then we'll find the area between A and B. So these are the steps involved, correct? So let A be the shaded area which is bounded by the curve, the x-axis, and the moving boundary PQ. So this is PQ, the moving boundary, right? Within this interval of A to B. It is within A to B. Okay. So in that case, we just learned that the dA dx, rate of change of area, is equal to the function itself. So that was the fundamental theorem of calculus, correct? Part 1. So we'll equate straight away the equation with rate of change of area and finding the integral. We are going to solve by the integral. So area is equal to integral of 3x to the power of 5 plus 3. So x to the power of 6, denominator 6, which cancels with 3 and gives you half. And here we get 3x plus c. Now to find the value c, notice that if this particular point is like shifted inside and it's right there, in that case area is going to be 0. So when x is equal to minus 1, the left boundary condition, then the area is 0. Substituting the value minus 1 for x and 0 for a, we get the value of c as 5 by 2. So 0 equals to half minus 1, so minus 3 plus c. So c is equal to basically 3 minus half, which is 5 by 2. So we have the value of c, and now we have our area function, which is equal to half x to the power of 6 plus 3x plus 5 by 2. Now we'll substitute the value of the boundary condition, x equals to 2, right? So that is the boundary condition given to us, x equals to 2. So when we substitute that 2 here, we get the value, which is 40.5. And so the area under the curve between minus 1 and 2 is 40.5 units square. Is that clear to you? So we use this fundamental theorem where we have figured out that the area function is basically integral of the function itself. Correct? And so we applied this particular concept and found the area function. Now let's try to generalize the whole thing, right? So in this case, we are taking a general function. So finding area under a curve, but instead of taking, like we took minus 1 and 2 last time, so we'll take 2 points, the boundaries as A and B. So the example now is find the area of the shaded region shown under the curve y equals to f of x. We have a general curve between the curve, the x-axis, I should write very clearly, the x-axis, and the lines x equals to a and x equals to b. So that is the x-axis for you, correct? And then we have the curve, and this is the area in which we are interested. So we have a boundary which is moving, so the point P on a function f of x is being considered where the coordinates of point P are x and y. Okay, now from the fundamental theorem of calculus part 1, we know that dA dx is equal to the function itself, which is f of x. Now, when this point P is kind of like here, right? So when it is at this position A, in that case the area is 0 because it coincides, the width is 0, right? So at that stage the area is 0. So we can always substitute x equals to A, we get area equals to 0, substituting A equals to 0, x equals to A, area equals 0. So when you write A equals to x equals to A, you get f of A plus C equals to 0. That means C is minus FA. So we get the area function, which is f of B minus f of A. When x is equal to B, in that case, this goes to B, sorry, this is f of x, not b at the moment. Now we are going to substitute x equals to b, so it becomes f of b minus f of a. So area basically is difference in the definite, indefinite variable, indefinite integral values at the points b and a, correct? So we have shown that the area of the shaded region can be evaluated by the integral from a to b of f of x d of x, and that is equal to f of b minus f of a. Is that clear to you, right? So that is the definition of definite integral, right? So another way of writing this notation is we can write f of x with the boundary conditions from a to b. So that really means f of b minus f of a. Is that clear to you? So here we have shown that the area function is the integral of the function itself within the two boundaries. Condition should be that the function should be continuous within this integral in this boundaries, right? That is the condition. Let's see formally how do we write or state the theorem itself. Now, when you want to state the theorem, you have to put the exact wordings, and that is why we are rewriting it. The fundamental theorem of calculus part 2, which we just derived, is if f is a continuous function on closed interval a and b, then the integral, the definite integral from a to b of f of x d of x is f of b minus f of a, where f is any antiderivative of f. In other words, derivative of f is small f, right? So f prime is if equal to f. So that is the fundamental theorem of calculus. Clear? Now based on this, let's have two more examples. So here we have example number 5, which says find the area of the shaded region shown under the curve of f of x equals to 16 minus 3x squared. So that's the curve. Between the curve, the axis, and whenever I write axis, in this case, it should be x-axis, okay? And the lines, the vertical lines, x equals to 1 and x equals to 2. So these lines are shown here, right? So that is how it is. And from our fundamental theorem of calculus, we know that the area is equal to integral, definite integral from 1 to 2 of the function itself. The function is 16 minus 3x squared. So integrating, we get a equals to 16x minus x cubed. Lower bound is 1 and the upper bound is 2. So the area value is substitute 2 and 1, find the difference. And once you find the difference, you get the area as 9 units square. And that is how we actually calculate the area under the curve. So I hope the concepts are absolutely clear. And that is how we actually perform this particular calculations. So once again, we began with a simple example of a line, and from there we showed that the area is actually dependent on the integral of the function. So area under the curve between the x-axis and the two vertical lines is actually given by the integral function itself. And from this concept, we actually got the fundamental theorem of calculus, which really connects derivatives with integrals. I hope you understand and appreciate it. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time.